So we spent the last couple lectures carefully defining our kinematic variables, and I know this is getting a little old and perhaps a little slow. In the beginning, that's what the physics is. We've got to get these definitions out. So we talked about the distance variables, and we talked about the average velocity and average speed. Well, we're still on the velocity variables, believe it or not. And so we now have to talk about what's called instantaneous velocity. Remember, we have average speed, we have average velocity. These are the definitions. We spend a lot of time on those. What is instantaneous velocity? Well, average velocity really doesn't tell us a whole lot about what we're doing at any time, right? So let's say I drive my car from here to Charlottesville. Take my car out. Let's just assume it's one-dimensional motion. It's a straight line trip. But I drive at 20 miles an hour down my street. I get to the traffic light. I stop. Just sort of illustrating not terribly well, but here's my car driving from Lynchburg to Charlottesville. I might drive slowly. I might come to a stop for a moment. Then I get on the highway. I drive faster. I hit some traffic. I drive a little slower. I get off an exit and I drive really slowly. And I come to a stop at a traffic light before I get where I'm going. Right? So my speed is varying the whole time. But what is my average velocity when I go to Charlottesville? Again, let's just assume that this is the plus x-axis. We're traveling along the plus x-axis, and Charlottesville is 60 miles away. And let's say that I take a total of 75 minutes. Delta t is equal to 75 minutes. And so, x initial is 0, and x final is 60 miles. So my average velocity, v average, is equal to plus 60 miles over 75 minutes. Which, if I want to put it in terms of seconds, actually I just said put it in terms of seconds. I'm not sure why I want to do that, right? So I can just divide 60 miles by 75 minutes, and it's 0.8 miles per minute. You might say, wait, but when we drive cars, we measure in miles per hour. It doesn't matter what units we're measuring. We can turn this into miles per hour if we want. We can just do a unit conversion, right? We can multiply that by 60 minutes in 1 hour. So therefore, it's 60 times 0.8, which is 40, is that 48? 24, 48, yeah, 48 miles per hour. Okay, so my average velocity is 48 miles per hour in the plus x direction. And that's my average velocity. But that really tells us nothing about the fact that in the beginning of the trip, we were going 20 miles an hour. On the highway, I was going 75 miles an hour. I came to a stop in a number of places, right? I came to a stop. I was going 0 miles an hour, right? I mean, v equals 20 at that point. V equals 75 at that point. Miles an hour. I'm not writing down the units because I'm trying to do this quickly. V equals 0 here. V equals 0 there, etc. V equals 10 miles an hour when I got off the exit. So that average velocity really tells me nothing about my velocity at any instant. So what's an interesting variable to describe motion is really the instantaneous velocity. What is my velocity at any instant? And so we need to know how to calculate instantaneous velocity, the velocity at any instant. Of course, that can be a hard thing to do sometimes, depending on the situation. But in general, we can talk about how to calculate instantaneous velocity. Instantaneous velocity is my velocity at an instant. So v instantaneous, velocity at an instant, is defined as my average velocity over a very small amount of time. Average velocity over a very small amount of time. So if I talk about my average, so at any instant, right? If I talk about my average velocity at that instant, my average velocity just over the last moment is going to be my velocity at that instant. If I'm talking about my average velocity since the trip started, that doesn't tell me what my velocity is right now. But if I just talk about my average velocity since a minute ago, or since a second ago, or since a millisecond ago, that's going to tell me my average velocity. So the instantaneous velocity is defined as the limit as delta t goes to 0 of delta x over delta t. You say, ooh, how do I calculate that? Well, sometimes it's easy, sometimes it's not. But in notation, that is what's called dx dt. So the delta turns into a small distance over a small time, and in the mathematical notation for a small distance and a small time is a little d. instead of a delta. Delta is usually a larger distance, change over a larger distance. D is a small distance, so dx over dt. And for those of you who know calculus, you know that this is just the derivative of x with respect to time. It's the derivative of x with respect to time. Now, the derivative for us here is, remember, derivatives, for those of you who know, and for those of you who haven't done it yet, don't worry about it. I'm going to have to teach you. Derivatives are rates of change. So what the derivative is, delta x over delta t is a rate of change. It's a rate of change of displacement with respect to time. The derivative of x with respect to t is a rate of change over a small distance. So it's the instantaneous rate of change. It is how is the value changing right this second, instead of how is the value changing over time, over a long time. So that's what derivative is. It's how is the value changing at this moment rather than how is the value changing over a long time. So what does that mean? When you're talking about how fast the value is changing, right, you can talk about anything that changes, right? Derivatives are super important in life in general, in understanding rates of change, right? It's important in economics, it's important in science, it's important in anything that you're measuring and you're curious as to how it changes or whether it's going to change. It's important in your bank account. Rates of change, right? How fast is your money growing? How fast are you saving? How fast are you spending? It's important for your credit card bills, etc. Food, right? Let's say that over a day, you might eat 2,000 calories, right? So is 2,000 calories per day is your average rate of calorie intake. But what is your calorie intake at any moment? When I'm out on a run, right, my calorie intake is 0 because more often than not, because I typically don't want to eat while I'm running. Whereas you get all your calorie intake at one time. I eat 1,000 calories in a sitting and in 30 minutes, right, for my lunch. And so that rate of calorie intake changes. It's 0 at times. It's 1,000 divided by 30, 1,000 calories divided by 30 minutes at some time, etc. Those rates of change are happening all around you, and it's really important to understand rates of change. So let's just think about the car trip. Let's think about the car trip. And let's just pretend we're going in a straight line so we can talk about one-dimensional motion. We'll get to two-dimensional motion another time. And let's just say I start at my house, and my house is at the origin, right? My house is at the origin. And then I change my position, right? I drive down the road, and it takes me a certain amount of time to drive down my road, right? And at the end of my road, then I'm at a certain position, and it took me stop it. Sorry, my pad is acting up. Okay, it took me a certain amount of time. And then I get on a highway, and I'm going to drive a lot faster, and so I'm going to cover a greater distance in the same amount of time, and so, I'm going to go faster. And then I'm at a traffic light, or I hit a traffic jam, and so I don't move anywhere in a certain amount of time. So I'm just saying, let's just take some certain amounts of time, delta t1, it doesn't matter, delta t2, delta t3, maybe they're all approximately the same amount of time, and where am I after that time, right? So I'm just graphing my position versus time. So again, I'm going to move relatively slowly coming out the gate. I'm going to move faster on a faster road. I hit a traffic jam and I'm sitting still, right? Because the position is on the left axis. My x-axis is actually pointing up here because I'm graphing it versus time. And then I get going again, and so I go at some speed, and then I get to where I'm going, right? And so this is my final position, x final, x initial. So, so what's my average velocity? My average velocity, right, V average, is x final minus x initial for t final minus t initial, or just x final minus x initial over the total time elapsed, delta t. My average velocity is just x final minus x initial. Let's draw it in a different color. So x final minus x initial, it's that distance, and t final minus t initial. This is t initial, this is t final, and so it's over that time. It's the slope of the line that points that starts of the line that starts from the origin and finishes that starts from my initial position and goes to my final position. It's the slope of that black line, right? That's the average velocity. But my instantaneous velocity, let's say, here is less than my average velocity. My instantaneous velocity here is greater than my average velocity. My instantaneous velocity here is 0, right? And so what is the instantaneous velocity? The instantaneous velocity is just my average velocity over a smaller amount of time, right? The instantaneous velocity is just the slope of this line. My instantaneous velocity is the slope of this line. My instantaneous velocity is the slope of that line, and my instantaneous velocity is the slope of that line, right? V equals 0 is the easy one, right? This is V less than V average at the bottom. I don't know. But anyway, so my instantaneous velocity, which is the derivative of the position versus time, is just the rate of change at an instant. It's the slope at an instant. It's the slope of my position versus time graph at a certain time. That is something that we could do graphically if we have a graph. Sometimes we can do it analytically if we have a function for instantaneous velocity. But I'm just going to leave the definition at that, and we'll come back to it with some examples later. We've got to get these definitions out, and this has taken me a while. The one other thing I want to note is that instantaneous velocity is the most common velocity variable we use. So instantaneous velocity is just v. We drop the inst, right? There's no subscript on the instantaneous velocity. You can write inst if you really want to, but while v average is v average, that's kind of a silly way to write it, instantaneous velocity, we just drop the subscript and use v. So when you see a v without the subscript, we're talking about instantaneous velocity. Okay, the last kinematic variable, so we had distance, displacement, position, right? Distance, position, displacement. We had average speed, average velocity, instantaneous velocity, and then we had acceleration, right? The acceleration is a measure of how the velocity changes, right? The velocity is a measure of how the position changes, or displacement, rate of change of displacement. Acceleration is a measure of how the velocity changes, rate of change of velocity. So in the same way, we have average acceleration, and average acceleration is delta v over delta t, the change in velocity over change in time. Which velocity is that? That is the instantaneous velocity, delta v over delta t. And in the same way, we've got the instantaneous acceleration, which is just a, these are definitions, which is defined as the limit. How does the instantaneous velocity change over a very small time, right? At an instant, delta v over delta t, and that is dv dt. It's the derivative or the slope of the velocity versus time graph. It's really important to understand that this means the slope of the velocity versus time graph. And when we wrote, right, that velocity is dx dt, that this is the slope of the position versus time graph. So you need to be able to read these off a graph. You need to be able to look at the slope and just talk about it. So for instance, let's say that I have a position versus time graph that goes like this, right? So now this is one-dimensional motion. It's just saying that the position is changing at a high rate, is changing at a lower rate, right? The position is not changing at all, position is changing at a higher rate, etc., right, as we go along this graph. So you can say, oh, well, if the velocity is the position versus time graph, you can tell me how the velocity is changing, right? The velocity is the slope of the position versus time graph. What is the slope at the start, right? What is the slope here, right? The slope, remember, is the tangent line. And the slope here, right, at this point, well, I'm not doing a good job of indicating which points these are. Let's just put some points on the line. Red point there, red point there, red point there, red point there, red point, red point, red point. I don't know. These are terrible, terrible graphs. Okay, so let's just look at the slope. Let's draw a tangent line at each of these red points, right? Tangent line, tangent line, tangent line. I'm drawing a tangent line at each of the red points. So now you can tell me, how does the velocity change? Because it's the slope of each of those green lines. Let's look at the very first red point. The green line goes up and down, right? It's got a really high slope, so it's a high velocity. Then as we follow this curve along, let me give a different color here. As we follow the curve, right, along, that's terrible. Out loud without drawing it, right? First red point has a high slope. Second red point has a lower slope, so the velocity is smaller. Third red point has a slope almost zero, so velocity is zero, almost zero. The next red point has a slightly higher velocity, so it's sped up again. Next red point has a much higher slope, so it's sped up a lot more. We're there, right? Well, I guess that's what I could have done, is I could have pointed at the points. This has a lower slope, so the velocity is slowed down again. This has a higher slope, so the velocity is sped up again. So what's happening as I follow the line? I'm going to go ahead and draw now and say faster. Whoops, no, that didn't work. Okay, there's a lot of mess on this page, but what I'm really getting at here is what's important here is that the average acceleration is that, the instantaneous acceleration is that. It's the same, defined in the same way that the average and the instantaneous velocity is defined in terms of position. So what's another term for a cold dog? A chili dog. What do you call a cold dog that's sitting on a rabbit? A chili dog on a bun. Okay, so let's do an example. Let's say, a simple example, right? Let's say I'm in my wonderful car, which always looks like, I don't know what, a top hat with wheels. And I'm driving to the right at 20 meters per second. And I slow down to 10 meters per second in 2 seconds. And my car gets smaller also. Okay. And it's t equals 2 seconds. Okay. What is my average acceleration? Not velocity. What are you talking about? Well, in order to do any of these problems, first of all, we do need to take into account direction, right? So if the right is my, if going to the right is my positive x direction, then I can say my initial velocity is plus 20 meters per second, and my final velocity is plus 10 meters per second. And so therefore, my average acceleration is equal to final velocity plus 10 meters per second minus initial velocity minus plus 20 meters per second. I'm just going to carry those pluses to indicate I've already accounted for the direction, and then the total time elapsed is 2 seconds. And so what's my acceleration? It's minus 10 meters per second over 2 seconds. Oh, of course, we didn't talk about units. What is that unit? Well, it's minus 10 over 2, which is minus 5, and it's a meter per second, or that is written as meters per second squared. This is the unit of acceleration. The MKS unit of acceleration is meters per second squared. In this case, we get minus 5 meters per second squared. What does that tell me? It tells me that I'm changing my velocity, or changing my speed, at 5 meters per second every second. I'm changing my speed by 5 meters per second every second. What does the minus sign tell me? The minus sign doesn't tell me I'm speeding up or slowing down. No, it does not. In this case, I am slowing down. But what the minus sign tells me is what is the direction of my acceleration. It means that I am changing my speed to the left, right? Because to the right was positive. To the right was positive. It means my speed is changing to left, meaning that I am speeding up to the left or slowing down to the right. We'll talk more about the signs later, but the sign is really important, right? This does not necessarily mean I am slowing down. It just indicates what direction I chose as positive. I chose the right as positive, so since I am slowing down to the right, then I'm going to get a negative sign, which means to the left. So the answer here would be that it's minus 5 meters per second squared given this axis, or it's 5 meters per second squared to the left. That's my acceleration. It's 5 meters per second squared to the left. The minus sign just tells me direction, right? It's 5 meters per second squared to the left. It means that I am slowing down to the right or speeding up to the left. We'll talk more about those signs later. But that's pretty much it. That covers all of our kinematic variables. It's a little bit of a mess. I'm going to bring it back together in the next lecture.